I don't remember it yet, like, that's why when I went to take it easy. I finished it. I finished it.
Some things are important.
No, it's just there might be a nail or a small leaking hole like fire, so I was asking for like advice.
Oh, wow. One of the things they do when you take it to the garage is they'll put like the tire, or I've seen it like you go to, if you have a bike, they'll put it in water so you can see a little
That's what he
trickling.
was telling me.
So if you just like put a little, try different places, just put a little water on the tire and see if you can see it bubble.
So, yeah, and then he told me to mark it with chalk, and then if anything, that's for fire, take it over there to like get it fixed or something.
Yeah.
Or I've seen videos of where it's like a replacement, it's like a little thing you lift it in.
Yeah.
And like locks it.
That's also what they'll do. They'll depressurize it, probably, take it off and push it out from the inside. And so it'd probably be more rigorous if you took it to a repair shop, other than trying to finagle it yourself, but, yeah, well, looking on the internet, there's amazing, maybe there's a way to do that you probably have to get all the air out of the tire, trying to figure out how to do it. I've also heard that there's like something you can put in the tire, kind of like, and it coats the inside of the tire. So it might be maybe a stopgap thing that you could consider. Oh, okay, yeah.
Or like deep.
Yeah. So, well, I'll wait for another minute or two, wait for David to come back, and we'll get started here. So it looks like we're gonna have a couple more warm days. I was thinking maybe we're all over our being warm, but maybe not. All right, well, we'll go ahead and get started. As always, I like to open up in prayer, and then I'll kind of give you a little sense of what we're going to cover for today. So, dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course and everybody in the ECS programs, Lord. Several are having some challenges with family or health challenges, Lord, and I pray that you would be ministering to them and bring them to wholeness. Help each of these students, Lord, to prepare for a bright future. Now they're investing the time and energy to provide for the education for their future endeavors, and I pray that you would help and guide them. Also help them in their spiritual formation, Lord, as they get a chance to really dig deeply into Scripture, understand the biblical concepts we want to be guiding our lives by, and the theological concepts that we pull out of that, and give them interesting and creative ways for faith integration. In Jesus' precious name, we pray. Amen. So we're going to be continuing our journey as we go through the way Stalin likes to be thinking about the best way to be thinking about computer architectures. And so we're getting close to be finishing this second section here in the textbook. We're going to be going over input and outputs today. And so I'll go over that in a few minutes and try and introduce that with my greatest hits section and then get into some more details. But before I do, just a couple reminders that I wanted to let people be mindful of. I'm starting to get some people that are responding to the student survey, and I'd really recommend that all of you do, because what that does, it helps me to see, are things working, anything that you might want to have in terms of a tweak. It's really trying to help you guys have the best way of learning this material. And I realize, myself included, when I was in school, like maybe you have a teacher, they teach one way and it's not your learning style. It makes it really hard. You probably really hate the course. So I'm trying to be a little bit flexible and have Tuesdays are different than Thursdays in terms of the modalities of what we're doing. But one of the things I did get was some feedback that we tend to have in the lectures a little bit more of a high level way of introducing the materials. But what about getting into more specific details? And so I have some very detailed lectures. These are different than the recorded lectures that we have via Zoom. This is a whole nother thing that was my summertime adventure, was preparing for this course. And so if you go to the Canvas for this class, and it's a very top one, it's called the chapter video lectures. And so these range like on the order of an hour for each chapter. And so it's a lot of details. And so because I have that, I've tended to try and not go in as much detail during our class time and have a little bit of a repetitiveness trying to build on the topics. And so by now, I think everybody is familiar with the von Neumann architecture, at least the name. And probably if I was to go around the whole room, you would be able to quote the three things that are part of the von Neumann architecture. So that's the first thing that I wanted to point out. Do take the time to take the student survey. It really helps me. So far, I haven't gotten too many responses, but it sounds encouraging that I think we're on track. The only other thing that I heard was that some of the chapters are kind of long. And so just going back to the content slide, the first chapter is kind of long, chapter 3 is kind of long, but I think after that, you'll see that the chapters are a little bit more reasonable in terms of the amount of material that's covered in a chapter. But that's anyway, that's the way that Stalling decided to lay it out. And then a commercial of sorts. I'm actually teaching a course in the spring. It's called System Engineering. And I just talked with Dr. Ye, and he said it's open for both engineering and computer science students. And so if that's an area that maybe you're kind of toying with, and I've seen both computer science as well as engineers involved in system engineering. It's the majority of my career was in that. And so it's kind of a nice platform to be able to think at a holistic, a high level way. And so maybe a way to think about it in a computer science sense would be like an architect, software architect. And so we get into some modeling techniques that, if you've ever heard of UML, well, there's another thing that's called SysML, system modeling language, rather than a universal modeling language, that we'll get a chance to be thinking about how we would go about modeling something. And I have briefly showed you some of the stuff that I did in chemotaxis with the first project, the digital logic. And that's actually a paper that I'm just about to submit for publication that really went through details of modeling a biological system using SysML. And so if anybody is interested in that, I can give you a heads up on how that's coming along. And I also have a couple of YouTube overview things that I have on. I actually have a YouTube channel. It's nothing that big, but mostly my lectures, recorded lectures, including the ones that I was pointing out here. I post them on YouTube and then have links so that you can get easy access through them in Canvas. So that's just a couple of things I just wanted to give you a heads up on. And let me just go ahead and walk through some of the details, the specifics. For this lecture, going to be focusing on input and output. And I'll do that via going through our greatest hits section and not going through some of these as much detail, but we see this von Neumann architecture. Stalling even talks about maybe a fourth element, trying to make a distinguishing between the input and output and the system interface of the system bus. So if you have like a motherboard, you've heard me use that term. Sometimes the way laptops are going, they call it just a system board. And so we've started to give you a little bit of insight in some of the hardware, showing you some pictures of some of my geeky stuff that I have at home. And so this is an example. All of this would be fitting into a backplane. So that would be part of that system interface. We talked a little bit about how things have gone over time in terms of computing platforms, some trends. And so that's always interesting to think about. We have a more detailed view of this von Neumann architecture. And when we get into the two sections from now, we're going to get really deep into how this works when we start to be thinking about assembly language, when we think about instruction sets, how we actually cause a programmable environment, which what we're trying to do with a computer to make it real and make it useful for what we're trying to do. We'll also be talking in more detail about this fetch execute cycle. And so everything needs to be set up. And so Thursdays, I've been starting to show you how that starts to work by single stepping through some assembly language programs through our Mars MIPS emulator. We talked about the different types of memory. We talked about the statistics, how things are a little bit different, the way that we have with instruction versus the random way that we use data in different parts of the computing environment. How this non-intuitive thing, but having more cache actually improves performance, so much so that is used again and again in different ways, what we see in computing systems. And so we got a chance to be seeing that. We talked a little bit more specifically, thinking about the random access memory and the different technologies. These three terms here are also in this other area where I've been doing some research in neuromorphic computing. And this is sometimes called memristors in that kind of an environment. The fact that it stores memory, but the way it goes from one memory state to another is actually another thing. And so in neuromorphic computing, instead of a von Neumann architecture, you have what's called computing memory. And so both the computing, the CPU functions and the memory are coincident, and you have the IO separate. We started to talk about how things are done with different technologies for larger storage devices like a hard drive. I showed you a MacStar hard drive, and it's old enough that you could actually get a little bit of a sense of the platters, of the round platters that are inside it. And there's multiple platters, and you have this kind of configuration that you have heads on the top and the bottom, so they're written on both sides of that. We had an introduction into RAID, and so what I think is the easiest one to get your head around, but it also takes the most memory, is the RAID level 1. And so it's actually, you put things on two separate hard drives, and so everything is mirrored. But using other things that we talked with different types of code, error correcting codes, you have a way of having other ways that doesn't take as much memory, but you have a way of keeping the integrity of your data larger than what you have with one disk. I've say this a lot, but it's really important that you back up your data. So some of the strategies I mentioned, having more than one computing platform. So if you buy a new computer, don't just throw your old one away. So that's a backup. Having a way of having backup. And so there's various ways of doing it, either online. I have a couple home servers that I do things there. And so make sure you do that as you have like your Google Drive. And so you could even just doing it manually once a week, if not more often, starting to copy what you have. Then we get into what we're going to be focusing on today is this type, looking at different IO modules. And so this is a high-level view that we've started to be thinking about. And so it's a device that translates information from the way that one piece of hardware sees it and another. And the focus of this is trying to engage with the external world in various ways. And so if I was to say, like, at least maybe half you guys have a Mac, and so you're probably familiar with the term Thunderbolt. We'll talk about that. USB, USB-C, that's the current technology. It actually has the same type of connector for a Thunderbolt or a USB-C. And I'll talk a little bit about some of my adventures there with some devices at home where I've been coming up with that. So that's a little bit of a high-level introduction to be thinking about the inputs and outputs. And now let's get into some of the details. And so we'll talk a little bit about the evolution of how IO has been thought. And so want to be thinking about the external devices, even like what I'm doing now. It's evolved a couple ways. And believe it or not, there was a time when computers didn't have a mouse. I can tell you for sure because I actually had to use them. And so it was a way of doing computing that's different. Well, now we have a mouse and we have like a pad that you probably have as your default on your computer. And if it's set up just right, you probably, even having a mouse is starting to get something that's a little bit passe, if you will. But let's start from that and then start to be talking about, well, how we start to be thinking about how this works, some basics, and then over time, how on multiple ways that Stalling talks about in the text, how performance, how a lot of people have been thinking about this for decades to improve performance of computing. So we have this general chart that I already mentioned in terms we have the address lines, the data lines, control lines, all of this are things that the system bus, and so say the IO module is trying to connect an external device, and that information has to be passed to memory, has to be passed and shared in the appropriate way with the CPU. All of that is stuff that needs to take place. So there's various categories of IO devices and human readable. You can think like I would be lost without a keyboard. You know, I can't think in my mind in a detailed sense. If I had to come up with what was the ASCII bit representation for A, rather than pushing a key, you know, you can see that would be taking a lot longer. So that's one way. So having the monitor, the keyboard, the mouse. There's also machine readable, XML. Maybe that's something that you've heard. And so, what are the ways that are not meant for us to be able to communicate, but it's internal? The way that the different type of buses are set up, it needs to be conveying that information, but it doesn't necessarily need to be something that I could actually read, if you will. We talked about magnetic disks and things like that. And then we need to be thinking about communication, passing information from point A to point B. So those are some generic things to be thinking about it. And as I was digging into this, I like to think of an IO device as like a translator or transducer. It converts from one format to another. That's is key to what is taking place in an IO device. And to be thinking about the keyboard and monitor, I remember reading a book about Linus Torvald, the person that invented Linux. And so he thought it was a huge success when he finally could get with he was trying to develop the Linux kernel, that he push a key and that the result of that would show up on his monitor. And so some basic things that we take for granted, but guess what? That's one of the first things that you would need to have working to know that you can engage with your computer. You can actually exercise control over it, like Control C, for example, Control Z. And so there's information passing. If you're writing a paper or something, you want to make sure that when you push the A key, that's what comes out. If you want to do an interrupt, say you're doing a command line interface, those are all things that need to be dealt with. And so there are character sets. I am mostly familiar with ASCII, but there's also the International Reference Alphabet. There's different ways that it's called, and that's one way that Stalling has mentions it, where everybody uses the same code. And so it's like everybody speaks the same language, if you want to be thinking about it in that way. And so you have to have those common standards, those interfaces, so it's just going to be universal. So those are the things that we want to be starting out with as a way of thinking about it. So the keyboard and mouse is the most common means of a computer user interface. You're starting to have a little bit more of a touch screen interface. And so we're getting more familiar with our phones and our tablets. And so that's another way that's starting to emerge. And the user provides the input through the keyboard, the monitor displays the results. And those are all the things that have gotten quite familiar with. So, so what are the major function of an I/O module? They fall into the following categories: control and timing, processor communication, device communication, data buffering, and error detection. We talked about how error correction is used in a lot of different areas, things that we're not aware of, but you want to make sure that you don't have things get messed up as it's going from one element in your computer to another, going to the next level, or you saved a program you've been working on for weeks. When it saves and you boot up your computer the next day, you want to make sure that it's the same as when you left it the day before. So all of those are things that help out with that. So we then start to be thinking in a little bit more detail of an I/O module. There has to be the control logic. What am I supposed to do? What am I communicating between? And what is the data that's supposed to be exchanged? Those are all things that need to be fleshed out and clearly delineated, so things are going to work as they're supposed to. And so this is just trying to give a cartoon way of thinking about that. And so you have two sides of this. You have the interface with the innards of the computer, and then you have the interface with the external world in whatever way that you're trying to do that. I think probably the very common one that we're used to dealing with, and I'll talk about in more detail in a few minutes, is a universal service bus, USB. And so you just plug something in and it auto detects what it is. Or if you're hooked up to the internet, it gets a driver and it configures it. I see this more on my PC than a Mac. And so you stick something else it hasn't recognized. It has to make sure that it knows how to work with it properly. And then it'll bleep up with a little message to say, it's all configured and ready to use. That's the type of things that happen. Well, in terms of I/O, there's a couple of different ways of how this could work. You can have programmed I/O, and so everything's orchestrated. You know when something's going to happen. And at times this can mean that you have to wait for something to finish before you go on to another item. And that can be a performance hit. And so that's one of the reasons why things have gone to interrupt-driven I/O. And so something says, this is top priority. Maybe you've gotten a little email and they have like a little exclamation mark on it, or it's a different color. It's just a way of trying to say, hey, you need to read this first. You need to act on this right away. And so that's the characteristic of what we see with interrupt-driven I/O. And then there's another thing, something called direct memory access. And so basically, you're letting that I/O device, it's streamlined. So under certain things, when they're set up, it goes direct writing to memory. And one of the things I saw with an older computer, the buffer that's used for your monitor is actually memory. So by writing to certain memory locations, it can actually go directly to having you view your favorite movie on an old computer. And so there was ways in the past that you could streamline that or enable that. Maybe you have to go into the BIOS and enable something, but that just gives you an idea what's going on with that. So I kind of giving you a little bit of an overview of what's going on with some of the major ways of doing the I/O. And so you have like the data, you need to know where, and then you need to know, well, what exactly am I supposed to be accomplishing? And so this can be the thing that we deal with the command side of it. So are you trying to control something? So you're given control of another device in your computing environment. Is this a test? Are you trying to ping something? Or are you trying to read or write? And so these are some of the things that are out there that would need to be taken care of. So I'm not going to go through this in detail, but these are 3 ways of talking about how you can engage with for an input of a block of data, but we mentioned this program IO, an interrupt version of that, or direct memory access. You can see that direct memory access is real short. For both the program and the IO, there needs to be some type of decision logic for passing through that. One, do you pass the resources so they can take the ball and run? And when is it not going to be something that you can do? So the CPU you can think is like the overall conductor, and it, as computing environments get smarter and smarter, the things below it, it's like the first lieutenants of this computer are taking on more of the load. And so it's more just of a coordinator rather than in the old days, it had to do everything. And so that's one of the things that has changed over time. So with program IO, there's a close correspondence between the IO related instructions that the processor fetches from memory and the IO commands that the processor issues to an IO module to execute the instructions. So we've just started to see this a little bit on Thursdays when I've been starting to single step through an assembly language program that you got to fetch thing out of memory, stick it into a register, and then you have to get all of the right registers configured. And then you say, okay, now we do the sys call. That's like one of the things we were trying to do, hello world as an example. This is the kind of things that are going on. We're getting a little bit more focused for the IO. And so maybe this would be like what I talked about. You want to be available whenever a character is pressed on a keyboard, that you're going to display it on your monitor. That might be the kind of a function that you're thinking about. So there's a couple ways of doing the IO mapping. You can have a memory mapped IO, so devices and memory share an address space. The IO looks just like memory read writes, and so there's no special IO commands, or you can have something that's separate. And so it needs IO or memory select lines. And so it's an either or kind of a situation. And those are some possible ways of how that could start to come together. Okay, I'm going to skip over some of these details, but this just gives you some of the specifics about memory mapped and isolated IO. And so what we're going to start to see as we get towards the end of this chapter is that as the IO gets smarter, you actually have like a sub computer that's actually dedicated to doing IO. You can be thinking like a GPU, for example. You know, it's a different thing, but it gets to give you an idea how the first lieutenants are getting smarter in a computer, and those are some ways where that's starting to show up. So the problem with programmed IO, you have to pull everything around a chain, and then you have to come back to it. It's not like something smarter that says that nine out of the 10 things hardly ever get anything going on. And so why waste all that time to go around that whole chain to do that? And so that's where interrupt driven IO has really shown to be a useful thing to do. We'll be picking up some of these themes with the Arduino when we have a cyber physical environment. And so you actually have real hardware, but you're programming that with your digital logic, you actually, in a sense, were programming hardware, maybe for the first time, and you've got a chance to see that. But you've seen that there's this hardware software engagement that all has to take place for this to work properly. And the interrupt process is something that has to engage in both of those fronts. This chart is, once you start thinking about it, it gets a little bit simpler, but basically you have like two time perspective of what's going on before the interrupt and after the interrupt. And so basically the computer is doing its thing, and all of a sudden it gets this interrupt, and it says what it has to do. It has to store everything it was doing, manage the interrupt, and then take everything from that was in all of its registers and put it back into the registers. And so this is what this is trying to give you a sense of what's going on. So you have your main memory, you have your registers, and so basically you're trying to show the some details of your memory and your processor and what happens during an interrupt. An interrupt takes place, and so everything that was in the general registers has to be pushed out to a dedicated place for where you're recording the registers. And so it's called, they put it into a control stack. And you then, instead of just going to the sequential, going through the lines in your program, you then manage this interrupt. And then when you're done, you do exactly the reverse. You take what you stored in memory, stick it back into the registers, and then you can continue on where you left in your main program. So that's what we're trying to illustrate with that diagram. So there are some concerns with IO interrupt implementation because there will be multiple IO modules. How does the processor determine which device issued the interrupt? So that's to be something. If multiple interrupts have occurred, how does the processor decide which one to process? And so you need to have a way of making sure that you say, hey, I send the interrupt, and so you identify yourself, and there has to be a priority scheme, what level of priority. And so if you have a high level priority and a lower level interrupt takes place, it says, okay, take a number, I'll get to you, but I have to handle this other one first. Those are the kind of strategies that are there that have to be available. So for device identification, there's 4 general categories. You can have multiple interrupt lines. So maybe everyone has their own dedicated, kind of like think of your old 2 cans and a string between them, if you will. So it's a dedicated line. You can have a polling, even with an interrupt driven. You can have a daisy chain, that's possible. Or you can have something that's using a bus arbitration to try and figure out where and how you're going to be doing that. And so Stalling does a good job of telling you some of the more easy to understand approaches, and then give you some perspective of some of these things that are a little bit more complex. And so I won't go into that in too much detail for that, but just at least have us be thinking about it. Okay, the next half a dozen charts are going to be talking about specific chips, and so Intel chips. And so starting to think, well, maybe you can have a whole computing environment for IO. Maybe a little bit short of that, you have like a dedicated microcontroller. That's a term that we will start to be using in the Arduino project that you'll get a chance to be thinking a little bit more about. And so this is what we're talking about here, is like a microcontroller, a dedicated chip. And so on a computer, on the motherboard, have you ever heard the word called a chipset? Is that a term that you've ever heard? So maybe a couple of you. This is where you start to be talking about the chipset is the motherboard. Stalling talks about the system IO. This is where it does some of this this level, a certain level of translation and passing information, routing of things. That's stuff that takes place in these kind of capabilities. And this is an example of a peripheral interface chip that Intel has. And so trying to think, I believe that my my Dell computer, a desktop, has an Intel chipset in it. I'm not positive what my Microsoft Surface has off the top of my head. And so we're starting to see some configurations that look kind of similar to what we're going to be getting into in assembly language and thinking about how a processor works. And so you have a word, and so the configuration 1 or 0 of some of these bits is going to determine the function that's actually going to take place. And so that's something that we see here. And so this gives you an idea of what the chipset would be doing for dealing with the keyboard and the display. And so this is using this chip, the 82C55A. And if you're interested, if you just follow the more detailed lectures that I've recorded, you can get some more specifics about how all of that works. So there's some good news and bad news about this. Drawbacks of programmed and interrupt IO. So both forms of IO suffer from two inherent drawbacks. The IO transfer rate is limited by the speed which the processor can test and service a device. So the CPU is just running ragged doing all this stuff because everything has to be routed through the processor. The processor is tied up to manage an IO transfer. A number of instructions must be executed for each IO. So when large volumes of data are to be moved, a more efficient technique is this. You just say, okay, I'm going to give you access directly to memory. I don't need to have everything routed through me. And so we just empowering the lieutenants to take care of some of this function. And that's a more broader view of what's taking place with direct memory access. So this is just giving us a little bit of a sense of what's going on with DMA. And so you can feel free to take a look at that in more detail. So I think those are some of the major things that I wanted to capture in an overview for this lecture. This is giving a high-level block diagram for an Intel 8237A DMA controller. And so this is another part that could be part of the chipset that's in your computer that maybe you are now just getting a chance to be introduced to for the first time. There's registers. So all of this is sounding like the same kind of terms we're going to be getting into for a main processing environment. We're now seeing that take place for an IO device, and it's starting to look more and more like a processor. You can have direct cache access. So not only that you can access to the main memory, but remember how a lot of times you have this interface before you get to the main memory is like, well, it seems like instead of going all the way to the memory, this is constantly being referenced. And so you can go like to your cache 1, your cache 2, your cache 3. And so this is a thing that starts to take place. It also starts to talk about how we deal with internet connections and Wi-Fi connections. And this is another theme that, as some of you have been tracking my fiber optic adventure at home, that we got this router that's both a Ethernet, so wired, and Wi-Fi router. It's actually a Wi-Fi 7. And so what they're quoting here are the maximum theoretical data rates for Wi-Fi 6, and I believe Wi-Fi 6E. And so this is something also called AC, AX, and Wi-Fi 7 uses the acronym BE, depending on which way that you're trying to express it. Like there's an IEEE standard, but I'll continue to be thinking a little bit about that as we go along here. So guess what? Ethernet, Wi-Fi are input and output. Okay, that falls into that category that maybe you had thought about is something that needs to be worked out. There's also I'm not going to get into this enterprise type of environment, but this is also something that Intel has, the Xeon way of how they deal with IO. And then we have some thoughts about the performance issues associated with cache related direct memory access. And so those are things that you we'll just skip over for now, but just have us be thinking about. Let's just try and have like a larger structure of how we're going to consider this. So now just thinking a little bit more about Ethernet, Wi-Fi, that falls into the category of IO. And so one of the ways that typically is done for this, and Cisco is like, really knowledgeable about this, and you have everything in packets. And I also mentioned something called PCIe. We covered that in an earlier chapter. One of the cards that I will be getting for my Dell desktop is a translator that goes from 10 gigabit Ethernets through a PCIe card that gets it into the computer. And all of that is happening through packets. And so the size of packets needs to be defined, and a lot of different things. And so this is what's going on with the packets that needs to be translated from what's going on from a communication environment to now the data processing environment that you have in a computer. So there's incoming, there's outcoming things that need to be managed. All of that needs to be thought through. And so when you have things that are going really fast, you can see that every little something that's going to slow things down is going to be something you want to try and avoid. So those are just some thoughts that I wanted to capture about that. And I'll focus a little bit on this slide. And this talks about the evolution of IO functions. And so maybe this gives us a way of thinking about how we go from pretty dumb type of things, and the CPU has to do everything. And guess what? That CPU is going to be working really hard. We then started to be thinking about having a controller or an IO module that can start to offload that. So you can either use programmed approaches. That was where we first started to do it. So like a daisy chain, go around the circle once every second, you sample. There's something you want. Okay, I'll get this. I'll get the rest of it in the next round. And then you have an interrupt version, which a little bit more efficient. That sounded good. Still, there were some challenges. Having direct memory access, that was useful. We also started to talk about having a way to engage with the cache. And then we can get this super smart type of module, having like a specific chip that does IO. And even yet, you can have an actual computer, your first lieutenant, maybe it's a captain now, and has just a whole bunch of capability that is now not taking any of the resources from the CPU. And basically, it kicks off a function, it sends it to its lieutenants or captains. And then when they're done, it reports back and says, things are fine, let's move on. And so that just gives you a rough sense of what's happened over time in the development of IO technology. So I think that's a whole lot. So let me pause for a second. Any comments or questions on what I shared? Okay, we talked about Ethernet, Wi-Fi, things that those fall in the IO category. We talked about the keyboard, the mouse, those fall in the IO. And here we have some of these things that are like this plug and play. I mean, now that's pretty commonly known, but like when you had like Windows 95, if anybody have ever heard of that, one of the first time that you actually had a GUI for Microsoft, Apple was ahead of Microsoft at that time. And so this is something that was just a huge breakthrough, that you have this common interface. It's fast, relatively speaking. You can see how this has evolved, USB 3.1. And if you have USB-C, like I said, it has the same connector as a Thunderbolt. And I'll have a separate chart on Thunderbolt, and it's slightly different. But we're getting close to like 10 gigabits per second with a USB 3.1 in terms of a transfer rate. That's pretty fast. That's cool. And so this is something I'm sure you guys are frequently using as you're doing different things in your computing environment. So that's the first one for us to be thinking about. Anybody, have you ever heard of FireWire? Have you ever used it? I actually had it on some older Macs that I had, and I never really seemed to use it. There was one like external hard drive that I had a FireWire and a USB connection, and I typically always just use a USB connection. So I'm not really going to talk about that, but that's something that has been out there that I think hasn't really caught on, at least in the circles that I've been. This is something that maybe you've heard of, SCSI. Sometimes when I do virtual machines and you're trying to think of how you're going to connect your virtual hard drive to your virtual computer, it'll use the term SCSI, but it's once again, it's something that really isn't that popular. So I won't spend too much time talking about this type of IO type of approach. Thunderbolt. This is something I remember the first time I had it on my Mac, and as I was just trying to scratch my head and figure out what, even like this one, I have 4 Thunderbolt connections on my computer and nothing else. And so like you need to have an adapter for everything. And so, but on the flip side, once you get used to it, that means that I have all the flexibility of making those ports what I would like. Since then, if anybody has like the Apple Silicon Mac, they've kind of gone back to what they had before. So they have an HDMI connector. They actually have a dedicated connector for the power. This one, I just plugged right into a Thunderbolt connector. And so you can just see, this is another example of how approaches have changed over time, what people do for different parts of the computing environment. And so I think Thunderbolt has a future that's looking very promising. One thing I'll show a little bit on our Thursdays sessions is I actually have this device that translates a 10 gigabit Ethernet to Thunderbolt. So I'm actually able to do that on my Mac. And this is where I got reminded that USB-C is not the same as Thunderbolt, because I tried to plug it into my Dell desktop at home, and it says, sorry, I don't speak Thunderbolt. So I'm a USB-C. And so if you do something on that kind of approach, then I can help you out. So this is another one that I won't spend too much time talking about. This is more things that are done on the server side, InfiniBand. And so that's another technology that's out there. And so this comes back to, well, here are some ways that you can be communicating externally. PCIe, we've covered this already. I've given you some anecdotal information of what's been going on for myself. And a common interface for a hard drive is something called SATA. And so the way how it worked, it was 1.5 gigabits per second, and then it went to 3 gigabits per second, and then 6 gigabits per second. I actually had some issues with one hard drive at home, and it would only negotiate to go to 3 gigabits per second rather than 6 gigabits per second. And so I said, well, since that's what I have the operating system on, I really don't want to use that. I want to have something that's going as fast as possible, because I don't want to have the throughput be the limiting factor for performance. I mentioned that I got a 18 terabyte Seagate hard drive. And one of the things in terms of this Exos architecture, they actually even mention a 12 gigabits per second transfer rate was also another thing that they have in terms of the possible things that you could be leveraging. So this is just some things that you'll be encountering when you're talking about input and outputs. Remember the thing I like about PCIe that I mentioned, it has like this dedicated point to point, but it's programmable. Okay, I need it for these things to be connected. And when you're done, then I could connect other 2 things, and it has like a dedicated, and effectively it's like giving you a quote hardwired connection, but it's actually not hardwired. Ethernet is still the backbone. Wi-Fi is wonderful, but guess what happens? Like at home, everybody in our cul-de-sac, I can see all their Wi-Fis, like we're trying to connect to the Wi-Fi. And it used to be 1 or 2. When we're sitting in our living room, which is like in the front of our house, I can see like 10, 15 Wi-Fis in the whole cul-de-sac. And so everybody's using that same bandwidth. And so what is the theoretical data rates that you can get versus what you're going to get? There can be a big difference between those 2. But Ethernet, it is a dedicated connection. And so 10 gigabits is now what I'm trying to work with at home. They even talk about 100 gigabits. I can remember when they had 10 megabits per second, 100 megabits per second for Ethernet, and then 1 gigabit. And so we can see how things are going faster and faster over time. I already talked about the Wi-Fi standards. And so here is the IEEE standard 802.11. And so they have like these acronyms. And so AC is Wi-Fi 6, I believe, and AX is Wi-Fi 6E. Maybe at home, you're just starting to get some Wi-Fi 6E devices. I know my MacBook Pro, I believe it's still stuck at AC. And so it has that kind of limitation in terms of its highest data rate. I'm hoping the next one I get is going to be this IEEE 802.11be, which is the Wi-Fi 7, which is what we got for our router. And it's still kind of coming out. It's not quite mainline, if you will, but there are a couple of devices that you can get that have it. Okay, well, that's a lot of information that I've captured. So I'm going to go ahead and stop sharing my slides for now and see if there's any comments or questions or things that you guys have that you'd like to spend while we're finishing up our class for today. So I think just about everybody's got your project 1 in. And so as I've said that you'll never get a lower grade if you want to work on it some more. But we're trying to give folks a chance to do some hands-on development in this course. And so now you've gotten that first one. It's easier. You're not going to blow anything up. It's kind of funny in past courses with the Arduino kits, you're actually plugging things in. And so it is a physical environment. And so you'll get a chance to get a little bit of a better sense of how things work, things you should do, things that you shouldn't do. But ultimately, you're plugging it into a USB device to your computer, and you got lots of different components you can use, so that won't be a big deal. So on Thursday, we'll continue to pick up there. I'll probably kind of wind down what I'm doing with the digital logic. I'll give folks, if anybody else wants to talk about what they put together. Some of the submittals that I've seen some nice complicated circuits that you've come up with. And so that's pretty good. And so basic to something a little bit more elaborate. That's what I was hoping to have people get a chance to get exposed to get familiar with what some of these digital logic devices look like with the way that we have the schematics. And so now you've got a chance to get a little bit of a sense of what that is. We're going to be seeing that in this next section. And so this will be a little bit of review since we've had our lab time a little bit ahead, but we'll talk about that digital logic. And we'll be talking about how we characterize numbers in computers. And so that probably, we won't get to that until the earliest next week, but that's something that we'll get a chance to be thinking about. Okay, any other comments or questions? Let me check online to see if there's Oates, Samuel, Andre, any comments or questions? Okay, that sounds good. But of course, I'd like to see you guys here in class. So it also makes it a little bit easier to chat if you wanted to have a sidebar. But I know that some things come up, and so I think I'll go ahead and end the formal lecture for here, and I'll stay around here for a little bit if anybody wants to ask any questions. But thanks a lot, everybody. God bless. Thank you.